The generalized equation of the work energy theorem is that we have the work done by non-conservative forces is equal to the change in mechanical energy, which is the change in kinetic energy plus the change in potential energy, which so far, change in kinetic energy is always half mv final squared minus half mv naught squared. And change in potential energy, we could have a gravitational potential energy in there, we could have a spring potential energy in there, and later on we could have a magnetic or electric potential energy in there as well. But we don't know about those for the moment, so we'll leave them off. So we're gonna work through some example problems here where we can apply the work energy theorem. Some of these problems are problems that we could have solved using kinematics, but now we can solve in a different way because we know the work energy theorem. So let's say, and some of the problems we couldn't solve using kinematics. So let's take one first that we can solve using kinematics. Let's say we have a ball is dropped from a height of 2.6 meters off the ground. What is its speed when it hits the floor? Now, this is a problem we could, you plug in the acceleration due to gravity and just go straight into our time-independent kinematic equation, but we can also solve it using energy. And let's throw in neglecting air resistance. So we're not going to consider the effects of air resistance on this problem, which means that there are no non-conservative forces acting, meaning that we can plug in a 0 on the left side of that equation, and that's equal to half mv final squared. V naught is 0 because it's just dropped, plus mg delta y, and then there's no spring in the problem, so we can leave off the spring force. If we go to solve this, we can see that if we rearrange stuff, v final, equals, we bring this over to the other side, that gives us minus 2g delta y. The m's cancel out, and then we take a square root. So our v final, square root, now you might think that minus is a problem, times 9.8, but since we're going down, our y final is 0, and our y initial is 2.6, that delta y is a negative. So that takes care of that, and we get that our v final y is 7.1386 whatever meters per second, and that would be in the downward direction. We know. All right. Oh, but I just asked for speed, so we only care about the magnitude. Let's take another example of a kinematic problem. Let's say a ball is thrown from 1.7 meters off the ground with initial speed, 18 meters per second at an angle of 26 degrees above the horizontal. What is its speed when it hits the ground? Now, with kinematics, this was a complicated problem. We had to break that speed up into its components and then do equations with the y component and then go back and turn that into magnitude and direction. With energy, this problem becomes much simpler. We have work non-conservative, 0, because I'm going to say our resistance is not present, equals 1/2 m V final squared minus 1/2 m times V naught squared. V naught is 18, plus m times g times delta y, which is a minus 1.7 because it's going downward, and there's no spring involved. Our masses cancel out, and then we get a final velocity, 0.5 times 18 squared, minus 0.5 times 18 squared, minus 9.8 times 1.7. Then that's moved to the other side, and then we multiply by 2, and then we square root, and we get that its final speed is 18.902 meters per second. And notice that nowhere did this angle come into play. In order to do this using kinematics, we had to break it down into components and whatnot, but this angle didn't come into play at all in this problem because because there is no angle in the energy equation. The direction doesn't matter when you're squaring it. There's another problem that we could solve using force and kinematics that, again, is easier to solve using energy. If we say a block slides 1.9 meters down a frictionless incline, that is at 17 degrees above the horizontal. What is its speed? At the end of this time. And again, we could write out our Newton's second law, find the forces, to figure out the acceleration of the block, and then plug that into a kinematic equation. But with energy, this is much easier. There's no work being done by non-conservative forces, and we've got 1/2 mv final squared minus 1/2 mv naught squared plus mg delta y. Okay, well, our V final is what we're trying to figure out. V naught, 0. Delta y is a little bit tricky because we're at a 17-degree incline and it's going 1.9 meters, but that's not too hard. Our delta y then becomes 1.9 sine 17, and it's negative because the final is lower than the initial, and then 9.8. Our m's cancel out. We've got a 2 thrown in there, and then we move to the other side, so it becomes positive, and our V final is that. And so, non-real answer. Why is it a non-real answer? Am I in radian mode? Oh, I'm in radian mode. So our V final is 3.299, etc. meters per second. Did I plug in? Okay, good. That's the first angle I've plugged in, so there aren't any wrong answers because I was in radian mode. But see, that problem is much easier to solve using energy than doing Newton's second law and then applying Newton's second law.